Hello, I'm Dr. Scott Steedman, and this is a series about my heroes, fellow engineers and the greatest structures they built on Earth. The tallest, the biggest, and the most expensive buildings ever built. The kind of structures that beg the question, how did they build that?
In our first program, we travel to Paris to take a look at the Eiffel Tower and then visit the Grand Serre, one of the finest examples of late 20th century structural engineering. But our story begins at the spectacular Garib Viaduct in the heart of France. The development and mass production of iron and steel in the 19th century radically transformed the nature of engineering. These newly plentiful materials offered pioneers undreamt of opportunities to bridge any expanse and scale unbelievable heights. Alexander Gustav Eiffel was one such pioneer. Born in Dijon in 1832, he trained as a chemist, but a curious twist of fate drew him to the burgeoning railway industry. It was in building bridges and viaducts that he made his name, and that reputation won him a commission to bridge the gorge at Garib.
The Garib Viaduct, here in the Massif Central in the heart of France, was the finest of Eiffel's bridge designs. A spectacular bridge built with mathematical precision, this viaduct illustrates the best of the new, bold civil engineering which emerged in the 19th century.
The viaduct at Garib was to be the highest iron arch bridge in the world. This design was an ideal way to span the steep gorge. A 563-metre-long railway deck sits on an enormous arch which straddles the Truyère River below. Eiffel used wrought iron because no other material had the strength and reliability to make the viaduct possible and allow the relentless progress of the railways to continue. The giant arch is pinned onto huge concrete abutments that are built onto the sides of the valley. The weight of the bridge passes down the arch into the abutments. The deck stands 122 meters high above the bottom of the gorge.
Engineers at that time did not have access to the complex computational methods of today, and they had to design a structure which they knew they could analyze. They had a shrewd idea of the direction of forces and the strength or resistance of materials, and their structures reflect that fact closely.
Eiffel opted for iron trusses for the huge arch, supporting piers and railway deck. A simple element, the iron truss is easy to analyze and can be used in almost any situation.
The whole truss has to be stiff enough and strong enough to carry its own weight and the weight of a train. The whole truss works like a beam trying to bend. So the top is in compression, it's being squashed, and the bottom is in tension, it's being stretched. The crisscross members in between work in either tension or compression, and one of their key functions is to keep the top and bottom in position. The stiffness of the whole bridge comes largely from the distance apart of the top and bottom, the depth of the truss. The bridge is made up of giant trusses, but within the giant trusses, there are also smaller trusses. It works on just the same principle. The top and bottom pieces, which carry the bending forces, are held apart by this cross-bracing in between.
All the pieces for Garib were prefabricated, brought to the site, and then riveted together.
It's like a giant Meccano set. Riveting was a skilled job. Must have been quite hairy doing it out here, this height. Riveting is a good process, though, and the rust that can develop around rivets can help actually fuse it all together. It's a nice system for bonding metal. Let's go on. Eiffel was very concerned about wind forces, and he carried out experiments to determine the wind resistance of different sorts of truss. Here on the Great Arch and up there on the piers, you can see that they flare out, which gives the bridge the lateral stiffness that it needs to resist the fierce winds that funnel down the gorge. Eiffel's method of construction of the arch was ingenious, requiring no scaffolding underneath. Instead, he built each side up from the concrete abutments as two cantilevers suspended on steel cables from the piers on either side. The whole operation was extremely precise, and when they finally met in the middle, only a very small adjustment was needed. Finally, they put the deck over the top. You can feel the whole bridge vibrating under the weight of the train. Quite a funny feeling, really. Yeah, it's passed over now. Wow, that was quite exciting. Staircase is wobbling, but that you could feel these main girders vibrating quite strongly. Eiffel calculated that under the weight of a train, the center of the arch here would deflect just 8 millimeters, about that much, and he was proved exactly right. In a traditional arch bridge, the weight on top is carried down to the arch through the spandrels, the solid part between the deck and the arch, which you can see in the masonry bridges on either side. Here, solid spandrels would have been so huge that Eiffel's engineers concluded the forces would be incalculable. So they opted for no spandrels at all, and instead used this great depth of truss bent into the shape of an arch to give the bridge the stiffness it needed to carry the trains. The most dangerous moment in any construction project, in terms of the project as a whole, is often just before the construction is complete. Eiffel must have been very relieved when the two halves of the great arches were finally riveted together, and he'd accomplished his dream, the biggest iron arch bridge in the world. With the completion of the bridge at Garib, Eiffel's reputation as one of the greatest civil engineers of his time was complete. It's a working bridge, of course, functional, like all of Eiffel's structures had been up to that time. Such a simple form of construction. Eiffel must have wondered how far he could go with it.
Paris at the end of the 19th century was the second largest city in the world, a city of wealth, a city of empire. There was a mood to celebrate the centenary of the Revolution of 1789 and France's new global status. A universal exposition of industry and commerce, a grand exhibition, was launched, and it needed a centerpiece. The invention of the lift and new skyscrapers in America must have inspired Eiffel. He jumped at the chance to build a huge and lasting monument, the Eiffel Tower.
Of course, the images that we have of the Eiffel Tower are usually from a distance, and it's not until you get underneath it, like this, that you really realize how huge it is. And the feeling of space under these great symmetrical legs is very impressive indeed.
Eiffel used 250 men to build the tower, and his engineers produced over 5,300 drawings of all the component parts. As at Garib, everything was prefabricated and all the holes were pre-drilled. Parts were then brought to the site where they were lifted into position by cranes and riveted together.
Must be very exciting going up in the lift. They were just recently invented. Quite exciting today, really.
To a Parisian in 1889, the highest thing you'd ever have been in would be a 7-story apartment block, like the ones down here. This is a waxwork of Eiffel in his office at the top of the tower. He was very interested in scientific experiments, and one of his justifications for the tower was the study of the lower atmosphere. Although Eiffel's obviously closely associated with the tower, in fact, it was originally conceived by two of his engineers, Monsieur Koechlin and Monsieur Nouguier, who'd sketched out a scheme for a super tower as early as 1884. Of course, they were all railway engineers, really, so they used the techniques they knew best. And what this reminds me most of is a gigantic railway pier, and we're right inside it. Eiffel's tower was to be the tallest structure in the world. Only iron or steel would be strong enough and rigid enough to support itself to these heights. Steel was a relatively new material, so Eiffel opted for what he knew best, puddled wrought iron.
Eiffel had an excellent and reliable source of top-quality iron in the foundries of Lorraine. Good quality iron was important because his whole reputation depended on the success of the project. Eiffel had made a deal with the city. He would put out 5 of the 6.5 million francs it would take to construct the tower. In return, he would keep revenues from visitors during the exposition and for 20 years thereafter. It was a massive financial gamble and the biggest risk of his career. So in order to ensure a profit from the venture, Eiffel had to keep his overheads down.
And one way Eiffel could keep costs to a minimum is to standardize as many of the components as possible. Looking up to the 3rd level, you can see many of the lattice girders are identical. Under each of the main floor levels are huge girders which span across the tower, tying the legs together. That's what makes the distinctive gaps in the lower levels of the Eiffel Tower possible. Looking up here from the 1st level towards the 2nd level, you can see the 4 legs very clearly. The weight of iron in the structure is 7,300 tons, and with the lifts and the other equipment, the weight of the tower in total is over 10,000 tons. Finally, back at ground level, behind me is the base of one of the legs, disguised with stone. If we go over to the north pier, we can get a closer look at the foundations. Inside the stone base of the legs, each of the 16 ribs sits in an iron shoe resting on a concrete foundation. The shoe carries a weight of over 600 tons here, and the thickness of the iron is 100 to 150 millimeters, about the same as this thickness here. During construction, each of the ribs was secured to the foundation using these bolts to stop them bending over as they were built up. Hydraulic jacks inside the shoe were able to align the structure perfectly. I don't usually go for this kind of thing, but there's something else I want to show you. The towers come to symbolize Paris, but it's the curved shape of the legs which is so well known. The obvious shape for a giant railway pier would be straight, like this. or inclined. But to resist the wind loading, these shapes would have to be braced to ground level. The wind acts on the side of the tower, trying to bend it over, just as if the tower was fixed to a wall and its weight was trying to bend it down. The curved shape of the legs acts like half an arch, carrying the force directly down to the foundation, so there's no need for bracing.
Eiffel's entrepreneurial skills made him a very rich man, but more importantly, he made a major contribution to the image of modern France, for which he is duly recognized. His tower was the last great wrought iron structure, which at the time represented the cutting edge of engineering, an ultra-modern building in a classical city. Since then, Paris has built on its reputation as home to some of the most spectacular modern structures, although iron is no longer the material of choice. On the other side of Paris, in the northeast corner of the city, is a structure that represents the very best in modern engineering. Almost 100 years after the Eiffel Tower was built, President Giscard d'Estaing decided to establish a new museum, the City of Science and Industry, to enable the French people to discover the industrial adventure of today and to celebrate the very best in modern science and technology. The museum was completed in March 1986.
This is a wonderful museum, a mixture of exhibits and exhibitionism. These great trusses on either side could have been plucked straight from the Eiffel Tower, but they look huge even for this building. But that's not why we're here. We're here to see the work of one of the greatest structural engineers of the 20th century, Peter Rice. The late Irish engineer, Peter Rice, was one of the most brilliant of his generation. He was instrumental in the realization of projects as varied as the Louvre Pyramid and the Sydney Opera House. Rice was invited by the architect, Adrien Fansilbert, to design Les Grandes Serres, 3 massive glass houses intended to unite the museum with the park outside. The spacious units represent the pinnacle of refinement in steelwork. They are light to the point of seeming to lack substance, making even the airy structures of the Eiffel Tower and Garib Viaduct appear bulky. The contrast between the heavy industrial trusses inside and these beautiful, refined glass serres is total. From the engineering perspective, this is what makes the building so remarkable.
The structure of the glass houses is light years ahead of the Eiffel Tower, but still beautifully simple.
Glass is in fact a very strong material in its pure form, but in practice it's rather weak and extremely brittle and breaks in an explosive way when any scratch or defect, however microscopic, causes a stress concentration. Steel can take huge loads in tension and compression, and it has the property of ductility. It will stretch before it breaks. This gives protection against overloading, a sort of warning, if you like, that the material is about to break. The challenge is to bring these two very different materials together.
Each of the 3 serres has 24 steel frames which hold 16 glass panels, each one 2 meters wide by 2 meters high. The 16 panels in each frame weigh 2 tons.
Carrying that vertical weight and coping with the wind load from outside is what this lightweight steel frame and connections are all about.
In simple terms, the glass plates have to carry their own weight and the force from the wind outside. The glass plates hang one on another
and their weight is carried right up to the top. There's a spring up there which locates the top panel. The wind force is taken completely separately through this stainless steel cable truss. The two systems are totally independent, and they only come together in the tubular steel frame around the outside. The connection is really very clever. Inside each of these 5 points is a ball and socket joint, inside the glass here and inside this metal unit. Like a hip joint, a ball and socket joint enables the glass sheets to move independently, so the whole system is articulated. This is the tubular steel frame that surrounds the glass walls. You can see where the glass meets the building itself. There's a flexible seal, and the joint here is free to rotate, so the whole wall can move inwards with the wind.
Rice had a great admiration for the 19th century engineers like Eiffel. He talked of their structures as having a simple honesty that goes straight to the heart of the physical characteristics of the material. But his own work is more Swiss watch than railway pier.
The meticulous attention to detail and sophisticated calculation in this design allowed Rice to refine every element. Like a racing yacht, each component has a precisely defined function. There's no excess baggage. There's some irony then that in a museum celebrating science and engineering, Rice's brilliant and innovative design isn't acknowledged or explained anywhere.
Rice also believed that the role of the engineer extended to building structures that people warmed to and that conveyed a feeling of having been designed by one who cared.
Rice's genius for structural engineering is clear. He had a mission to enrich people's experience of the structures around them, which is where he differed from Eiffel.
However, both Rice and Eiffel were like artists, masters of their materials and the knowledge available to them. But new materials and techniques are evolving all the time. Who knows what brilliant structures people will be enjoying 100 years from now? Next week, we look at the nature of defence. We start at a dramatic medieval Scottish castle, travel to France to see a spectacular fortress, and finish at the massive barrier that protects the people of Holland from the sea.